So welcome to Math383. This is lecture 23. And what I want to do, I'm going to change this a little bit over here. I'm changing things a little bit. So geometric series, primes after an analysis review. So again, whenever possible, I want to try to fix some of the gaps and just do some explicit details of analysis results. These are going to be extremely useful going forward. Most of you are not going to use the specific material, or if you happen to be in that situation, you can just take a book, learn the material at the time. There's a lot of results in complex analysis. What's really important to me is the thought process of how we attack things. How do you come up with what you want to study? That's what I really want to focus on. So we talked about these nice functions, xi, alpha, defined on the bottom, and the question of, we know it maps the unit disk to the unit disk. It's one-to-one, it's onto in the unit disk. We know that points on the boundary get mapped to points on the boundary. How do you know everything is hit? And so one way is to try to use some results from analysis. The continuous image of a compact set is compact. I just did some searching online. I'm posting the stuff here. I'm going to go through and do an explicit proof right now in a little bit more generality. And so let's assume we have the following theorem. So F from the unit disk to the unit disk is a one-to-one onto, so it's a bijection. And we'll assume F extends, and of course it's holomorphic. And we assume F extends to a holomorphic function beyond the disk on some open set omega. Okay, it's still holomorphic. Okay. And my claim, then if we look at F from D bar to D bar, all points on the boundary of the unit disk are hit. Okay, so we have a function where on the interior, we know it maps the interior of the unit disk to the interior of the unit disk, and everything is hit. What happens is we try to extend it to a map from the boundary to the boundary. So let's talk about the proof. Without loss of generality, assume we miss a point on the boundary of the unit disk. What point should we miss? 1, right? Because if it's not 1, just apply a rotation map and rotate the point to be 1. Okay, so we can always apply a rotation so that the point would be 1. Okay, so let's imagine what we have now. We have our unit disk here. We have our map F. We have another unit disk here. We have some point 1 that's not hit. I can choose a sequence of points that are getting closer and closer to 1. And each one of them has to have a pre-image in here. I don't know where those points are going to be. Maybe Z1, Z2, Z3, Z4, and so on. Anybody want to give me a specific choice for the points over here? What should the nth point be? So yeah, 1 minus 1 over n. So maybe Wn is 1 minus 1 over n. So that's going to give me a sequence of points. So the limit as n goes to infinity of Wn equals 1. And we'll let f of Zn equals, that's a terrible n. F of Zn equals Wn, or Zn equals F inverse of Wn. Is there a unique inverse? Why? It's a bijection. So a unique inverse. So now we have a sequence of points Z. So I have sequence of points Zn such that f of Zn equals Wn is going to 1. What do we know about the points Zn? So what's true about the point Cn? So we have, Zn is a sequence of points with f of Zn equals Wn goes to 1, and all the Zn live inside the unit disk. So if I have a sequence of points, what must be true? What must any sequence of points have? Convergent subsequence. So we have a subsequence Znk in the disk such that the limit as k goes to infinity of Znk equals, let's call it Z star. Where does Z star live? No. In the closure of the unit disk. So the unit disk is not compact. So when we look at it, it's got to converge to something, but it's got to converge to something in the closure of the unit disk. Yes.
Why are we taking a subsequence instead of just arguing the sequence?
We don't know that the sequence itself converges.
Oh.
So I'm passing to a convergent sequence, so I know I have convergence. I may not need to do this, but it gives me more to play with. I now know that I have a sequence of points that converges. What can you tell me about f, the absolute value of f of Z star? Is less than or equal to 1 as each absolute value of f of Z and k is less than or equal to 1. We all agree that it has to be less than or equal to 1 in absolute value. Each of the Z and Ks is sent to something that is less than 1 in absolute value. So when I take f and I take the limit, it can't jump above it. It's possible that it might get to 1, and that's how I go from a less than to a less than or equal to. But I know everything in my sequence is bounded by 1 from above, so in the limit, it's got to be bounded by 1 from above. But the limit could be attained, yes.
Why do you know that Z star is in a constant?
No, D bar is the closure of the unit disk. It's the interior plus the boundary. So this is D union the boundary of D.
But why do you know it's on the boundary?
I don't know that's on the boundary. I'm just saying it could be it could be inside. We'll see that there's a contradiction if it's inside. At this point, I know that the Z and Ks have to converge to something.
Doesn't maximum modulus say it has to be in the boundary?
So we would get that now if we know that the value of f of Z star is 1, then maximum modulus will imply that's on the boundary.
But it might not be 1.
But it might not be 1. Well, but what do we know about the Z and Ks? We know f of Zn is Wn, and Wn is tending to 1. So eventually, it's got to be greater than 1 minus 1 over n, right? If we just go far enough down in the sequence, that f of Z and k equals W and k is 1 minus 1 over nk. So for all k such that nk is greater than or equal to big N, we have f of Zn k in absolute value is going to be greater than or equal to 1 minus 1 over n. So just keep going further and further down in the sequence, and you can get, it's going to be within 1 over a billion of 1. It's going to be within 1 over a quadrillion of 1. It's going to be 1 over a quadrillion factorial square of 1. Right? So we can get lower bounds as close to 1 as we want by just going deeper and deeper into the sequence. So what's the only possibility for f of Z star? 1. So f of z star in absolute value equals 1. In fact, more should be true. What does f of z star equal? It equals 1, right? We have a sequence of points such that when we apply f, it's getting closer and closer to 1. When we pass through a subsequence, it's still going to be getting closer and closer to 1. By continuity, it has to be 1. So you can later analyze the proof and see if I've put in some things that I don't need. But just because the function is continuous, as the z and k's approach z star, then the f of z and k's have to approach f of z star. The only possibility for f of z star is 1. If it's not 1, I'm converging to f of z star. And so if f of z star is not 1, eventually I've got to be a little bit away from 1, and that violates the construction of the z and k's. So this is just from continuity. I'm not using anything from complex analysis here. It's just if f of z star does not equal 1, then f z and k is a small distance from 1 for all k large. And that's a contradiction, because it's got to be convergent. So we know f of z star equals 1. Where does z star live? On the boundary. Why? Max modulus. So if z star is inside the disk, then max modulus implies f is constant. Contradiction. So this proves that we must obtain the point z star, the point 1, from some input on the boundary. So if we want to get a point on the boundary, it's not coming from the interior of the circle. Well, no shit. We know that the interior of the circle gets mapped to the interior of the circle. There's no way the interior of the circle can be mapped to the boundary. So the only chance to get something on the boundary is from the boundary. And what we've just shown is you give me any point on the boundary, and I can find a sequence of points, and I can get some point on the boundary that will be mapped to that.
So where do we use the condition that f extends to a homomorphic function beyond this?
Maximum modulus principle.
But we only need f to be homomorphic inside the unit disk, because
So I got to be very careful in terms of how is the maximum modulus principle proved? What is it assuming about f on the boundary of the set? And what does it mean to be differentiable on the boundary when you only you may only need f to be differentiable on the boundary and in the interior, and not on a strictly larger set outside. So I am being a little bit safe, and I might be assuming a little bit more than I need. The function that I have in mind, this C alpha function, we know, I guess I got to go back to another one. We know that this function extends to being a holomorphic function on an open disk containing the closed disk. So in the situation we're going to apply it, the assumption I'm making is not unreasonable. It might be enough to just assume that we extend to a holomorphic function on the boundary, or maybe even just a continuous function on the boundary. I do not remember specifically what is the condition needed for the maximum modulus. So good, someone is opening their book to see what is the condition for the maximum modulus. Thank you. And I will just try to just pontificate for a while as people flip through the books as to exactly what condition do we need to invoke the maximum modulus. But by saying that it extends a little bit more like that, I'm definitely keeping myself safe. Okay. So this is the analysis proof that shows that we get everything. What was the ruling? What's the?
Good.
So do we have to be on an open set containing the boundary? So what is it saying for maximum modulus?
In a region omega.
Right.
So you can obtain the maximum in omega.
Okay.
Doesn't say.
So I'll check as to whether or not the function has to be defined beyond. Okay. Right. So I mean, again, it might be sufficient for the function to be holomorphic in the interior and extends to a continuous function on the boundary. Now, here's my question for you.
Open set.
Open set containing the region omega? We're not going to spend time on this now. All right, we're going to listen. Here's my question. Does F map the boundary of the disk to the boundary of the disk? We know that it can't map anything on the boundary of the disk to something outside the disk. Because imagine you map something outside to something outside the disk, to say of absolute value 3. Then in a small neighborhood of your point, you would have to be in a small neighborhood of 3. And then that would mean that something inside the disk would be mapped to something outside the disk. And that'd be a contradiction. So you can show that you can't map to something of absolute value greater than 1. But could it map something on the boundary of the disk to something of absolute value 1/2?
No,
Why not?
because we started with the holomorphic bijection just on the interior,
Good,
which is so it's 1-to-1.
good.
Something on the back.
Good, so if something on the boundary maps to the interior, then if you draw a small little ball about that, you should also get something. So can you somehow get a contradiction? Yes.
Continuity argument, the inverse image of the interior of the codomain has to be an open set.
Okay.
If you had for the boundary on the inverse image of the interior, then it wouldn't be an open set.
Okay, so
And in a continuous function, the inverse image of open sets have to be open.
right. And so
If it contained a section of the boundary, if you neither open nor closed, then that's a contradiction.
but so I guess my question is, could the boundary of the disk be mapped to something like this?
Then the interior wouldn't, the inverse image would still not, the inverse image of the interior of the disk,
Yes.
when you do the pullback of that, you get.
Well, but I mean, but I would still have open. This would still be an open set on the right. I just have the slit coming in. Yes.
Let's just look at the inverse function defined by f because it's a bijection.
Okay.
And then just use maximum marginal principle in that case. You know that's one more. You know that's a bijection, so it satisfies the criteria.
Okay, so if some point in here gets mapped to the interior,
Then some point in here will get mapped to the boundary. Some point in the interior here will get mapped to the boundary. And so you get a contradiction with maximum.
okay, good. Good. So I think we have several proofs that it has to map the boundary to the boundary, that it cannot be mapped interior. It's not a bad idea to try to write this up rigorously, and depending on how much analysis you remember, there's different things. I always have to slowly stop and pass to make sure things are done correctly. I'm not saying that what you said was wrong. I just have to stop and pass it very carefully. There's lots of ways to get contradictions. There's not just one proof here. And so again, if you're a little bit rusty in your analysis, try to write this up carefully and try to write this up in some sense maybe minimally. What do we really need? When are we using holomorphic? When are we just using continuity? We saw that earlier in the semester. We saw a lot of results where we assumed the function was holomorphic. Well, actually, we just needed, differentiable or even just continuous in some of the places to show that some of the terms didn't matter when we were on this quest to prove Cauchy's theorem. And we were doing all these expansions. We had Gross's theorem, and at one point we needed something to be small. We just needed continuity. Okay. All right, so what I want to do is I want to shift now to number theory, to the Riemann zeta function. And so again, I apologize. Normally I bring a basketball net and we play the game, but as I've had to occasionally rush to Mount Greylock with no notice, I don't really want to bring large objects here. If people want to play basketball later in the semester, let me know and we will arrange a time. All right, so hopefully everybody has seen the geometric series formula before. If the absolute value of r is less than 1, then when we sum 1 plus r squared plus r cubed and so on and so on and so on, we get 1 over 1 minus r. So you should have seen proofs of this. This is a truly, truly wonderful sequence to study. And the reason, or one of the reasons that's so important is if I give you 1 plus r squared plus dot 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 plus r to the n minus 1. And then I add r to the n plus r to the n plus 1 plus dot dot dot. This part over here is just r to the n 1 plus r squared plus dot dot dot. The tail of a geometric series is just r to the n times the geometric series. And this allows you to do a lot of wonderful things. You could actually use this to solve a lot of expressions without too much trouble. All right. So what I wanted to, oh, good. It's subscripted everything here. All right. So the walker was not working correctly, so I fixed, oh, and this is going to be wrong on all the subsequent slides. Oh, well. All right. So in some cases, you can actually prove some of these results by telling a story. So if I take r equals 1/2, here's a simple way to prove that the sum converges. Every time the person takes a step, they're covering half the distance from where they are to 2. So they start at 0, they take a step, and they're now at 1. And so this will go a little bit slower because I've got to upgrade all of these. They take another step, and they move closer again. And again, each time they walk, they move half the distance. So it should be clear that when you do this, that in the limit, when r equals 1/2, the sum of 1 plus 1/2 plus 1/4 plus 1/8 is going to just be 2. So this is proof by story. Can you do a similar story if you're taking steps of size 1/3, 1/9? Yes.
Yeah, so that sort of us to say that this is sort of like the limit that finishes, but like in story format, in where you're saying that, but because you switched to like talking about the shrinking of the remaining distance, it's sort of somehow more intuitive than just the idea that like it's started above.
Right. And here we also need to know the target. I'm talking about the shrinking distance to the target. If I don't know where the target is, how do I know how far I am from it? Well, this is where divine inspiration comes in. We know it's 1/1 minus r. Okay. Everybody should have seen at least one point in their life the algebra proof. You write out the finite sum going up to r to the n, you multiply by r, and you shift everything over. It should be screaming at you what to do. What do you do? Subtract. And what is it called when you subtract? What do you have? There's a special name for the type of sum when you subtract. Telescoping. So it's a telescoping sum. You have tremendous cancellation, and all the terms vanish but the first and the last. And so we get 1 minus r times Sn equals r to the n minus 1, or just trivially, we get Sn is 1 minus r to the n plus 1 over 1 minus r. And then if we just let n go to infinity, if the absolute value of r is less than 1, then we just get 1/1 minus r. And we could write this if we wanted to as 1/1 minus r to the n plus 1 over 1 minus r. And you can clearly see here's the limit 1/1 minus r, and the rest is just a little bit of a pollution. It's how much we're missing by in the limit that's going to become negligible. So has everyone seen this proof at some point in their life? Right. Sometimes in Algebra 1, people don't actually prove this, and they just state it to the students, and so glad that people have seen this. All right. Cultural extra credit. Name the players. Yes, I am old, right? So I will use the people from my childhood, Larry Bird, Magic Johnson. They're going to play a game of basketball. The first one to make a basket wins. They will alternate. And these are two of the greats of all time. So we will assume they never tire. And they will always shoot with the same probability of success. Would you rather shoot first or second? First, right? First basket wins. I would like to shoot first. We want to calculate what is the probability that Bird wins. So I'm going to let Bird's probability of making a basket be P. I will let Magic's probability be Q. I could do P sub B and P sub M instead for Bird and Magic. A lot of times people use Q for 1 minus P. I'm just choosing to use a different letter for each one of them. Okay. Let's let X be the probability that Bird wins. Can somebody tell me how you could calculate the probability that Bird wins? Yes.
I think it's like E plus, what is it? 1 minus P times 1 minus Q times P.
Okay, good. So you're first saying Bird wins on his first shot with probability P.
Yeah.
And then you're saying that he wins on his second shot with probability 1 minus P, 1 minus Q times P. Okay, good. And so you're just marching down the line like this. And we can calculate the probability Bird wins on his nth shot, and then we just add them all together. And you can't win on your first and your fifth shot, right? Once you win, you win. You don't keep playing to humiliate the other person, right? But sometimes it's actually easier when you're analyzing things to do that. If you're trying to calculate the probability that somebody wins in a best of 7 series, maybe just assume that 7 games are always played. And maybe the team has won the first 5 games. It might just be easier to do the algebra that way. But for here, as soon as you get a basket, it's over. Let's let R be 1 minus P times 1 minus Q. And then if we let R be that product, then the probability that Bird wins is P plus RP plus R squared P and so on and so on and so on. So R is the probability that they both miss. And so if we just factor out the P, we get our geometric series. So if we knew the geometric series formula, we could now calculate the probability that Bird wins. What we can do is we can use this to come up with an alternate proof of the geometric series formula. And it illustrates a wonderful principle. Okay? So this has definitely occurred in a lot of game theory. And that's why I wanted to show you this. So let's calculate the probability that Bird wins. So clearly, Bird could win by shooting and getting a basket. Now, if Bird doesn't get a basket, Bird misses, and Magic must miss, or Bird has no chance to win. So once Bird and Magic have missed, what is the probability from this point onward that Bird wins the game?
1 minus the probability that he already won the game. Something.
Close. You're close. It's just X. Right. It's a memoryless process. So once they've both missed, it's like we've just started the game. So there's a lot of times when you're trying to deal with infinite sums, which can be a real pain, where you can turn them into a finite sum by saying we have a memoryless process and a lot of things just vanish. So this is just going to be X. Well, now that we know that this is just X, we can solve for X. That's not so bad. And so I will replace 1 minus P, 1 minus Q with R. And so I can solve for X, and I get X is equal to P over 1 minus R. But we know X is P times the geometric series. So when we substitute that in, we now get our geometric series formula. So you can get the geometric series formula as a consequence of the memoryless process. Okay, and so let's look at what we did. So initially, I gave you the geometric series formula when the absolute value of R is less than 1. Did we prove that here? Why not? I saw at least one head shaking. Yes. They're probabilities. So because they're probabilities, what can you tell me about the range of 1 minus P times 1 minus Q? 0 to 1, right? So I claim that with a little bit of work, you can actually adjust this proof to get the result if R is negative, if R is between -1 and 1. But you can't really, complex values would be a little bit more interesting. If I gave you a complex number where the phase was a rational multiple of 2 pi, you could do it. I don't know if you could do it in general. So if you want, as extra credit, try to figure out how you could use the fact that you know the geometric series formula when R is positive to deduce it when R is negative. And again, the reason I like this is to try to see how much can you milk a result that you have. Once you have something, what are the consequences? How far can you push this? So you can push this to hold for negative values of R. If you're brave, see if you can push it to hold for complex values of R. How far can this go? Okay. So what I want to do now is switch to prime numbers, right? Hopefully everybody here has heard of prime numbers, right? This is in fact what motivated a tremendous amount of complex analysis, is people were trying to understand the distribution of prime numbers. And there's a wonderful quote, something along the following lines: frequently the shortest path to truths about real numbers involves a detour into the complex plane. It seems absurd that if I want to understand something like prime numbers, which are just integers, which are these real quantities, I need to work with the square root of -1. Why would we do this? Can anybody think why we would do this? Yes.
So that like all polynomials have root is sort of
So
like
good. So one thing is we get polynomials have roots. Good. What else? Contributors. We've just spent a couple of weeks dealing with all these wonderful consequences of complex valued functions. And so a lot of times what you can do is you can take something that maybe is defined over the integers and you can extend it to be defined over the reals. And now maybe you have a continuous differentiable function. You can use tools of analysis to analyze it. The same thing is true here. We can take something maybe involving the integers, extend it to complex inputs, and now all of the machinery of complex analysis is available. That's why stuff like this is often done. So what I want to do is talk a little bit about how we can go from the geometric series to studying primes. All right. So the first thing is, how do you define a prime number? So a lot of times people say a prime is a number that's divisible by 1 in itself. That is not a good definition because that definition would allow 1 to be a prime. So we want to have at least 2 distinct prime factors. In fact, we want to have exactly 2 distinct prime factors, yourself and 1. The reason we want 1 to be a unit is if 1 is not a unit, we lose unique factorization. This is the fundamental theme of arithmetic. Every number can be written uniquely as a product of primes in increasing order. And if 1 is considered a prime, then I can put in any power of 1 without disturbing things. Okay. Has everybody seen the Euclid proof that there are infinitely many primes? The copyright has expired actually millennia ago. This proof is over 2,000 years old. And so the standard argument goes as follows. Assume there are only finitely many primes, let's say 2, 3, 5, all the way up to Pn. And let's multiply all of the numbers together and add 1. So the product of P1, P2, P3 up to Pn, this is called a primorial. And we often write that as, Pn sharp is P1 times P2 ... times Pn. Can this number be divisible by P1? Why not? Then 1 would be a... So how would you phrase it? I would phrase it as the remainder is 1. Right? If we know the first term is the multiple of P1, 1 is not divisible by P1, so it can't be. Can it be divisible by P2? No, same reason. And so if you just keep arguing like this, it can't be divisible by anything on our list. So it's either going to be a new prime, which means our list was incomplete, or it's divisible by a prime not on our list, in which case our list was incomplete. So no matter what, this number can't be, this number shows that there has to be at least 1 more prime, and then lather, rinse, repeat, and just keep doing this. With a little bit of work, you can actually use this to get an estimate of how many numbers up to x are prime. So if we let pi of x be the number of primes p less than or equal to x, this gives something like pi of x is greater than something like some constant times log x. It's a terrible result. There are infinitely many primes, and they have to go at least at this rate. So if you want a nice exercise, try to actually make this explicit and get a lower bound for the growth rate. So the way you get a lower bound for the growth rate is you assume the worst possibility every single time. For the primes to grow as slowly as possible, what is the worst thing that could happen when we construct this new number?
That's the only prime.
It's the only new prime. And then when we do it again, what's the worst thing that could happen? It's the next prime. So just analyze the worst possible case and see what you can get. The actual answer is it's about x over log x. That's about how many primes there are up to x. This gives you log x. Nowhere close. Now, later in the semester, I will show you a proof of mine. I was able to prove that there's at least log x primes up to x. Better or worse than Euclid? Worse. Actually, it's much worse because one of the results I needed, I didn't realize when I first used it, it actually assumes the prime number theorem. So this is why I know you can never in your careers do anything worse than I did. So as an input, there are asymptotically x over log x primes up to x. I'm able to prove there's at least log x primes. Thank you. I'm here all week. Actually, no, I'm not. Now, I was able to eventually make the paper better, and then I opened up the proof which used the prime number theorem, and I removed the use of the prime number theorem, and I ended up getting a result that was good. But the initial result was terrible, and it's a great illustration of how careful you have to be when you're using results. Are you using results that are assuming things that you don't necessarily know? Okay. So let's analyze this construction. So if we start with the number 2, we add 1, we get the number 3, which is prime. So then we have 2 times 3 and we add 1, we get 7, which is. So we then 2 times 3 times 7 plus 1, we get 43, which is prime. What would you conjecture? Nothing. So you have taken enough classes with me. Well, but you've had multiple classes in complex. That's the difference between class and course are often overused, right? I used to do a lot of math with my son's classes, but I did it for too many consecutive years, and they realized eventually every game was rigged to my advantage. That's why it's much nicer to keep visiting, getting new kids each year. So do you think that the next one, 2 times 3 times 7 times 43 plus 1 is prime? Well, we can check, of course. And so if you do the next one, it does not turn out to be prime. So the pattern breaks down fairly quickly. And then thanks to Jacob, who sent the following, highly recommend this. This is by the 3 Blue 1 brown guy.
I don't know if they made it, but they published it.
They published it. And so it's a absolutely wonderful parody of the song Hallelujah about how patterns can fool you. It's worth listening to, and just the danger of extrapolating from too little information. There's a lot of open questions. So the question is, for instance, will it be prime infinitely often? The next prime we get on this is 13. What makes you sad about getting 13? We missed 11. Oh, of course, when we got 43, we also missed 11, 13. So what's a natural question you could ask? What primes do we get? Will we eventually get every prime? This will generate infinitely many primes, but as we do Euclid's algorithm, which primes will we get? How long will you have to wait? So this leads to the Euclid-Mullen sequence, which is one of the most difficult sequences to compute. It's basically what primes do you get as you do this? And you see, we get, after 13, we get 53, we get 5, the numbers get really, then we get 100, then we do get 11, the numbers get really big, 37. You have 107 down there, we have 31 over here. This is a strange sequence. So if you're looking for interesting sequences, if you're ever teaching real analysis or something like that to play with. And of course, there's 2 ways you could do this. When we had when we had 2, 3, 7, 43 plus 1, we have 13 times 139. We could take the smallest prime and add that to our sequence, or we could take all the new primes and add them to the sequence, right? I think it's more fair to take all the primes and just put them in increasing order as you get them, so that this should count as giving us 139. So you have to decide which way you want to do it. But what I hope this shows you is there are still open questions from some basic stuff about primes going back thousands of years. When I have something like Euclid's algorithm, I want you to be in the mindset of asking questions about it. Okay, it gives me infinitely many primes. What else does it give me? What does it give me about the rate of growth? What does it give me about how often it's prime? Is there any knowledge about what fraction of the time is it prime? Do we expect that that is 0 in the limit? Anybody want to conjecture? I have not looked it up. I have no idea what's known. I know what I would conjecture. How often do you think that the product of all the primes plus 1 is prime? 0%. I think 0% is extremely safe. I might even go so far as to say finitely often. Is that the primes there's infinitely many of them, but these numbers are growing beyond exponentially fast. The probability for them to be hitting the primes, I don't know. But the primes are a somewhat big set.
Are these still the only known elements in the sequence?
As of the last time I pulled it from Wikipedia, yes. I don't know if anybody has added anything since I've pulled this. This was from a talk I gave a few years ago. This talk was given in 2020, I think, during the pandemic. And so that might have been when I pulled this information. But these become extremely hard to compute because you've got to multiply all these numbers, add one, and factor it. And factorization is not easy. Sorry, factorization is not, no easy methods to factorize have been published. That is very different than saying factorization is hard. We think it's hard because no one has been able to do it. This definitely says as of September 2012. I don't know what's been done since then.
I feel like this isn't that.
No, it becomes extremely painful to deal with stuff like this. Okay, so hopefully everybody has seen the Riemann zeta function at least at some point in their life. You should know the Greek alphabet if you are a science major. So the main reason for posting this slide is just at some point in your notes, you now have the Greek alphabet. Okay, you should have the Greek alphabet memorized, ideally in order, but at least you should know what the Greek letters are. And as an aside, does anybody know what is the worst expression in mathematics to try to read?
I already had it spoiled for me. So.
Okay. So this is the complex conjugate of a capital C divided by C. Right. This is probably the worst thing to try to pass. All right. So you've hopefully done. Oh God, it's subscripted everything. All right, I will fix this with. I'll just go and take snapshots and whatnot. All right. So this should all be n to the s, 2 to the s, 3 to the s, 4 to the s, 5 to the s. So this is the Riemann zeta function. So it is the sum of 1 over n to the s. N goes from 1 to infinity. You should have seen this in probably calculus, maybe multivariable calculus, sequences and series. And they would call this, instead of doing 1 over n to the s, they would do 1 over n to the p. They would call it a p series, and it converges if p is greater than 1, or for us, s is greater than 1. We do not want to call this a p series because we want to always leave p for primes. Okay, so you should be able to prove these results from sequences and series, that the sum converges if p is greater than, if s is greater than 1 in absolute value, it diverges if s is less than or equal to 1 in absolute value. There are ways to elementarily prove this without the integral test. Okay, so what is the next integer after 2023? That was despicable. That was disgraceful. All right, after 2024. All right, that's much better. Okay, so we all agree there's really not much difficulty in finding the next integer after an integer. There was a recent post in Quanta about an explicit formula for the nth integer. So we can actually write down a formula for the nth integer. Okay, what about the next prime after 2023? If you're taking the Putnam this year, you should know that the next prime is 2027. It's always good to know what number near 2023, near the year you're taking it, is prime. After 2027, yeah, 2029, it's actually a twin prime pair. And so we luck out. It gets harder after that. The next one, we have to go a little bit further, 2039. The distribution between primes is much harder than the distribution between integers. And that is a huge question. The primes are the events we want to study. How long do we have to wait between events? And one of the reasons we love this function so much, and I will fix all these slides later, but for now, I'll just try to quickly do this, is if we look at the product, this is going to be terrible, but however. So if we look at the zeta function, it's the sum of 1 over n to the s. If I look at the product over all primes of 1 minus 1 over p to the s inverse, it turns out that that's the same as the zeta function, that these two values agree. Now we've talked a little bit about infinite products. We at least have some idea of how do we determine if something converges. Everything is going to be fine as long as the real part of S is greater than 1. And so are people fine with just understanding right now that everything should be exponentiated? And I'll fix that later. All right, so I will fix that later. It did not transfer the exponentials. Okay, so it's not immediately clear why we care about this, but one possible reason is we know the integers, right? There is no mystery in the distribution of the integers. For definiteness, can somebody give me the formula for the nth integer? F of n equals, thank you. All right, so the integers have no mystery. We even have an explicit formula for gaps between adjacent integers. Yes. And there's some group that's working on gaps between integers and their second neighbor. And they're making remarkable progress. And they think they can generalize it to gaps between k. Really easy problems. So the hope is maybe we can understand the sum. And if we understand the sum, maybe we can convert that to knowledge about the product. And the product involves primes. So maybe there's going to be some way to deduce information about the primes. And that's why we care about all of this. And so here's one proof. If we take S equals 1, then the sum becomes the harmonic series. What do you know about the harmonic series? It diverges. If there were only finitely many primes, what would be true about the product? Converges. Therefore, there must be infinitely many primes. You can even use this to get an estimate about how many primes there are up to x, because we know how the harmonic series diverges. If you sum the terms up to x, does anybody know approximately how large the harmonic sum is? Log x. And so if I have a product here, what would I want to do to this product? Log. And so if I take the log of the sum, that should give me like a log x, and that will essentially give me the sum of the reciprocals of the primes up to x is about log x. So that, yes?
You don't use it there in infinite number of primes in order to get this equality, right?
Correct.
Yeah, always.
So, right, correct. We used unique factorization. We used the fundamental theorem of arithmetic. Okay, so I'm going to skip that for now. So if we take S equals 2, then we get, we've talked maybe a little bit about this. This is pi squared over 6. And I claim that here's another proof of the infinitude of primes. If you use the fact that we know zeta of 2 equals pi squared over 6, I think I sent you a Lighthouse video of that fact. So if you know that, I claim there must be infinitely many primes. Because if there were only finitely many primes, then this would be a finite product of rational numbers, which is rational, and pi squared is irrational. So the irrationality of pi squared gives the infinitude of primes. What I did years ago is I looked at how irrational pi squared was and used that to deduce that there's at least log x primes up to x. And I was able to make that eventually better. To see why this is true, I'm going to just skip a little bit ahead. When I'm looking at terms by terms, if I have 1 over 2 to the s inverse, this should look like the geometric series. And we just expand each one of these factors out. And so when I'm expanding it out, I'll just do 2 cases. Again, I apologize that it's subscripted everything. If I have 1 minus 1 over 2 to the s, 1 minus 1 over 3 to the s, I multiply everything out term by term. And you can see when everything hits the 1, I'm just going to get the pure powers of 2. When everything hits the 1 over 3 to the s, I'm going to get 3 times all the powers of 2. When I have 3 squared, I'll get 3 squared times the powers of 2. And as I start to fill in, I've got 1, 2 to the s, 3 to the s, 4 to the s, 6 to the s, 8 to the s, 9 to the s. I'm never going to get anything twice because of unique factorization. Over here, I will get all the numbers that only have 2s and 3s in their prime factorization. It's not going to be the sum. It's going to be a subset of the sum. If I then throw in the factor coming from 5, I get even more terms. And so this is how you would prove that the product over primes is the same as the sum over the integers. It's just the geometric series formula. That's why I wanted to spend the start of today on the geometric series formula. This is going to be our fundamental object of study. And this connection between primes and integers is going to be useful to us precisely because of the results we have in complex analysis. All right, so I will fix all the slides and repost them later today. All right.